A very good morning, good afternoon and good evening to all the students and all those who are attending this course under MOOKIT NPTEL. The title of this course is Application of Forecasting, Regression and Time Series Models, and my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you are aware, this whole course is for 60 lectures, each lecture being for half an hour, and there are three broad areas which we had planned and which are covering in this course. The first one is in the area of forecasting, second one is in regression and third one is time series. So, we are doing the fag end of the last few lectures for multiple linear regression or regression models, and this is week 10. That means, we have already completed 45 lectures, which is 9 weeks completed and 3 more weeks to go, and this is lecture number 46. So, what is the coverage of this lecture and subsequent one? As you are aware that we have started nonlinear regression. So, rather than going to theory, we will just concentrate on different applications, give the overall functional form of these nonlinear models with the simulated data, try to show that how the best fit line along with the error being added, how would they would look like depending on different parameters which are very essential to be manipulated or to find out such that we get the best fit line. So, there are different models and we will go stage by stage. Number 2 is that as we are doing, obviously there would be a stress on how the nonlinear regression model looks like for different parameters, which will be highlighted. Plus, we will also go to the Excel sheet, which will be shared with you, as you are aware, and where you can change the parameters, check how the nonlinear regression models will look like. So, I will also go to the Excel sheet and switch between the PPT file and the Excel sheet as we progress with the discussion. The first one is, as you are aware, this is example number 35. We are going to consider the rectangular hyperbola model, which is the Michaelis-Menten equation is a rectangular hyperbola and which is given by the following equation, which I will first state and also state what are the parameters. So, the equation is given by of this form. So, as you know, y is the dependent variable and the nonlinear regression is in the numerator you have theta 1 into x and in the denominator you have theta 2 plus x. So, in the numerator is multiplied, in the denominator is added. What is theta 1? Theta 1 is basically the asymptote as x tend to infinity, because as x tend to infinity you will basically get the ratio which will give the asymptotic sense that what is the parameter value as you increase the value of x. And theta 2 is the x value given a response which is equal to theta 1 by 2 and epsilon is the error. Now, I need to basically spend some time about the error. We all know theoretically the average value or the expected value of the error should be 0. So, and also we also want to have a case or the error properties in such a way that the variance should also be minimized to the maximum possible extent. Obviously, if error is 0 in the deterministic sense or in the probabilistic sense in the long run, it is the best model which you have for yourselves. Hence, the data based on which we are trying to fit and also the case of the best fit line, which is the nonlinear regression line, obviously they would overlap such that the error component would be almost 0, but if there is an error I will try to point it out using the diagram which or the illustration which are there. Now, the epsilon actually, if you can recollect and in case if you can remember, generally it is normal distributed with 0 1 as the normal distribution for the error. Now, we can also have errors which has a mean value or expected value of 0 and the standard deviation can also be done accordingly. But there is an issue in the second case which I am going to discuss and I will basically utilize a different color to highlight that. So, if epsilon is discrete distribution between 0 and say for example, no, let it not be 0, because 0 won't give you the mean value of 0. So, consider this, it is between, just 1 minute, between -1 to +1. So, it is the discrete distribution, which means you will have the either the uniform discrete or you will have the uniform continuous distribution. And if it is uniform discrete, so obviously all the values are between -1 and +1 in increments of some values of k. K can be very small also, and if it is continuous one, it is continuous all the values between -1 and +1. So, obviously for this uniform discrete or uniform continuous distribution, the mean value, the expected value is 0, which serves our main concept or the idea that the mean value of the error is 0. So, the first big part is done. The second case is, in the case when we have the error as uniform discrete and uniform continuous, there the variability would be given by the formulas depending on if it is basically a continuous one, it will be b minus a whole square by 12, where b would be +1, a would be -1, and +1 minus of -1 whole square by 12 will give you the corresponding error. But if I consider the normal distribution, it would mean that you can have the normal distribution done in such a way that the error part which you have as you go more to the right, if you are looking at the normal distribution from your side or if you are looking from my side, onto the right, the errors or the dispersions will basically be more, but with a less probability. Similarly, for the left hand side, because both the normal distribution as well as the uniform discrete or uniform continuous distribution are symmetric with respect to the mean value. Now, in case if I want to have the probability for the dispersion of equal quantum, then obviously I will use the distribution which is basically uniform discrete or uniform continuous. In case if I want the dispersion values to be high, but with the less probability, then I would basically take the normal distribution and we will utilize that accordingly. And subsequent whatever I said, it will be done corresponding to all the subsequent models which we are considering. So, this is the first case. I will first show the diagram, then go to the Excel sheet. So, here we have basically along the x axis the x values which are simulated. By the way, we have used a huge amount of simulation data using very simple Excel data set, which you will see, and which I said which will be shared with you. Based on that, the blue line basically plots the actual best fit y, and the plots of the red dots which you see are the basically the actual values considering there is an error. Error means which I just considered. Now, for our case, to make our life simple, I have considered the error to be uniform discrete. Obviously, you can change it to normal distribution also. So, there is no hard and fast rule, depending on what assumptions you are considering, you will consider that, but to make our discussion very simple, we have kept it accordingly. So, if I go to the data set in the Excel sheet, we will first see for the case that for the first model rectangular hyperbola, plotting y and y1 versus x, considering theta 1 as 2 and theta 2 as 25, how does it look and how we can change. So, let me go to the Excel sheet which is already open. So, I will now zoom in more so that is visible. So, there are a lot of simulated data. So, if you go through them carefully, you will understand. So, the first data set, if you see, I will remove this. Remove this means just take them to the side, and the data set which you have is basically the rectangular hyperbola which we are considering, and this is the rectangular hyperbola. Let me zoom in a little bit more. Yes, now it is done. at least it should be visible. This is the rectangle hyperbola. The theta 1 value we will change. So, in the data set what we had, which is theta 1 as 2 and theta 2 as 25. So, let us make theta 1 as 2 and theta 2 as 25. And what is delta x? Delta x is basically, as I simulate the values of x, the starting value of x I take as 0.1 and then it gets incremented by 0.5. So, that is delta x is given by 0.5. So, the first value is 0.1, second value is 0.1 plus 0.5 is 0.6, 0.6 plus 0.5 is 1.1, which is the third value, 1.1 plus 0.5 is 1.6, which is the fourth value, and I consider accordingly. So, total number of data points which I take just for the simulation work is about 124. You can increase it. So, obviously, you will get a much better fit, more number of errors, and you can find it out. So, the x values, how they are simulated, it is explained. Now, what I do is for the y value, I utilize this formula. Formula was, if you remember, if I go back to the slide, it gives you in the numerator you have theta 1 into x, in the denominator you have theta 2 plus x 1. So, x the value. So, we check that. So, in the numerator it is theta 1 which is 2 into x, and in the denominator it is theta 2 which is 25 plus x, and the values are depending on theta 1 as 2 and theta 2 as 25. We have all the values of y as highlighted in column T. So, column S is the S values, x values, and column T are the corresponding y values. That is the best fit line, because we have not taken an error. Remember that we are just fitting the equation as it is. Here error for the best fit line we are considering is 0, because there is no undeterministic component there with respect to the reading. Now, what we do is that we add a component of error, and this component of error for very simple case we can take, as I have said, we can take the what we are doing is that we are generating a random number between 0 and 1 or -1 to +1, such that the average value would in the long run would be 0 and variability would be considered accordingly. So, we take the error and then add that value which is in T column, which is the actual best fit line, with the error and get the y1 value which is given in column number V. So, based on that I plot. So, the blue lines which you have is basically the best fit line, and the red points which you had are basically the y1 value which considers the error. So, based on that idea we generate and find out how the graph looks like. So, the graph which you have here is basically, again I am mentioning, considering the error as simple uniform discrete distribution or uniform continuous distribution, such that the mean value is 0, and we add that error to the best fit line to get the simulated data for the actual y1, and then check how the simulated data along with the values of the best fit line would look like. So, this is the best fit line. Now, obviously, I can change it. So, consider I go to the next graph. So, this is the graph which I have for the same case for the rectangle hyperbola, plotting y and y1 with respect to x, same equation theta 1 by into x in the numerator, and in the denominator you have theta 2 plus x. But now, we are changing the values of theta 1 and theta 2. Theta 1 we take as 25, theta 2 we take as 2. Very interestingly, now the error component basically has very less amount of dispersion. The mean value remains 0. So, dispersion. So, if you see the blue line which is the best fit line, I am sure this graph is visible to all of you, and if you check the values of y1 which are the actual fitted data which we are taking and trying to fit them with respect to the best fit line, you see the error component is very low, which means it depending on the values of theta 1 and theta 2 which you have to tweak, and you can take different values, you can get quite a good fit for this rectangular hyperbola nonlinear regression model. So, let us do that. in the Excel sheet with respect to theta 1 as 25 and theta 2 as 2, theta 1 as 25. So, just keep checking this graph how it changes, this one, theta 1 as 25, theta 2 as 2, and you find the best fit line comes out to be exactly what we have discussed in the Excel sheet, which gives us a lot of confidence that the model based on which we are trying to build up comes out to the case that as you keep increasing theta 1, the value of and theta 2 is decreased, you will get a much better one. Now, if you remember, when we had started discussing the rectangle hypermodel, I said that theta 1 was the asymptote, means that as x tends to infinity, in the Excel sheet what we have only about 124 points. So, once you get the Excel sheet, if you basically increase the data points x, make it about 1000 or 2000, the asymptotic value asymptote which you will get as x tends to infinity or to a very large value would basically come out to be theta 1. So, we are just simulating in order to double check that. The next value which we have is basically for theta 1 as 2 and theta 2 as also 2. So, let us check theta 1 as 2 and theta 2 as 2 here also, which means that a slight tweak in theta 1 to the lower side basically increases the variability, which means that the dependence of this rectangle hyperbola nonlinear regression model would be much better fitted when you consider the theta 1 value to be as large as possible. So, this is basically the case of theta 1 and theta 2 both being 2. Now, when we come to the other example, so this is the fourth simulation, I am considering both theta 1 as 25 and theta 2 as 25 also. So, let us make is theta 2 1 as 25, theta 2 as 25. You get the curve which you see here, this one, which is exactly replicated here. Now, interesting part is the type of fit, the decrease of the error is predominantly being dictated by the value of theta 1 rather than theta 2. So, if you would have noticed that, say for example, if I go back, theta 1 small, theta 2 large, theta 1 big coming out to be good fit, theta 1 small not a good fit, theta 1 large a good fit. But correspondingly, if you see theta 2 in this case which is highlighted here, it is 25, it is a large value, and in this case theta 2 is 2 is a small value. So, the preponderance or the overwhelming factor or the variable which is basically or parameter which has an effect on the value of the curve and its corresponding error is being dictated by theta 1. So, now if I consider a very large value of theta 2, let us keep theta 1 as 25, considered as 200. So, it becomes almost a straight line, because in that case the values as you fit 1 is theta 1 by x into theta 2 plus x for values, because as the denominator increases it becomes almost a straight line. So, now another important thing, as you keep fitting also check what are the y values, because in this case graph if you see the errors looks quite large, but if you concentrate on the y axis, the difference between these are in quantum of 1 unit, like 2, 3, 4, 5, 6 and so on and so forth it goes. So, if I basically consider the error values are hardly in the tune of about 0.1, 0.2 or 0.3, or maybe maximum it can go to about 1. So, a value of an error of 0.1 or 0.2 or 0.05 for this case would be quite highly appreciated. Now, for a value of 200 of theta 2, if I check and make theta 1 large, it was 25, let me make it 100. There you will see the preponderance and the overwhelming effect of theta 1 is slowly again coming to the picture, such that the errors are more small, because if you see the y axis now in the quantum of 5, like 15, 20, 25, 30, and the errors are hardly 0.1 or maximum 0.5 or 0.9. So, if you consider the case where you had theta 1 as 25, theta 2 as 200, that is case 1, and case 2 when you have theta 1 as 100 and theta 2 as 200. In case 2, the error concept, the mean value remains 0, but the error concept and dispersion of the error has been minimized to a large extent. So, let us make it, let us say for example, theta 2 let it remain at 200 and theta 1 let me make it as also 500. Let us see what it happens. So, here now the quantum which you have on the left hand side are increasing by on the y axis 60, 80, 100, 120, and there the actual data which is the red circled one and the blue one which is the actual fit almost merge, which means that the error dispersion is almost becoming 0. So, depending on the data set, you have to basically consider which value of theta 1 and theta 2 would give you the best fit in order to predict the rectangular hyperbola nonlinear regression model based on the assumption which you have. So, they are used in the case of chemical reaction, rate of reaction or concentration being given by parts per million, and the rate of the reaction would be basically given by y, and parts per million being the concentration which is being given by x. Remember, till now we are considering only nonlinear regression model for only one x, that means there is a single value of independent x. Now, let us go to the next example, which is the logarithmic model. And the logarithmic model looks like the linear regression model, but with a slight twist. So, a logarithmic model is of this form which you can see. Let me go to the slide show view. So, you have y is equal to theta 1 is a constant plus theta 2 into log of x, Neperian log. It would hardly matter whether you take Neperian log of base e or 10, and theta 2 is the shape such that when theta 2 is greater than 0, we have x increases, hence y also increases, that means positive proportionality. Thus, the curve is basically convex in nature, while if theta 2 is less than 0, we have x increases, would basically have y decrease, that means inversely proportion. The curve is concave in nature, and epsilon, as already discussed, is the error. So, with this, let us check both the graphs in the PPT file as well check in the Excel sheet. So, if I go to the first, so it is a logarithmic plot or logarithmic nonlinear regression plot of y, which is the best fit line, which is shown in blue. Y1 is basically the actual data based on the fact that we have the error, and error, as I mentioned, would be either case for uniform discrete or normal distribution with a mean value of 0, but the dispersion can be increased decreased depending on what you think the error property is. But the main property of error being 0 in the long run holds throughout the different simulations which are then being done. So, they are being plotted versus x values is there shown, and I am taking theta 1 as 20. So, remember theta 1 is basically a constant, and theta 2, if you remember, with a positive side or negative side, you will get the properties of the convex and concave set, convex and convex function, as already mentioned in the Excel PPT file. So, this is the curve, and if you see, the values which you have along the y axis are in quantum of 5, 10, 20, 25, 30, 35. So, the fit of the red points, which are the actual data, with the blue one, which is the best fit, is coming out to be quite good, and the error terms would be in the tune of, say for example, hardly about 0.5, 0.6. You can check the Excel sheet, it will clarify. So, if with this diagram, if I now switch on to the Excel sheet, so this set of values which you can see, logarithmic one is shown, logarithmic curve is also there. I will bring it forward. So, I will, so let us consider logarithmic one with theta as 20 and theta 2 as 4, theta as plus 20 and theta 2s plus 4. So, see the graph. The graph means this is the which you have here. So, these I have saved depending on as I made this simulation, had that graph and I then copy pasted them in the Excel sheet. So, look at the PPT file and then in the same tune go through the Excel sheet, that will clarify many of the doubts. So, again I am taking x value starting from 1, the delta x values gives you the increments of 0.5, you can change it, there is no harm. So, I have just made it a very generic one for the simulation, such that people can change the data, change the delta value, change the theta 1 value, change the theta 2 value, or change the starting value of x, such that you can have a whole gamut of different type of simulation, which will clarify many of the doubts how this different type of nonlinear regression model. First one was rectangular hyperbola, next one was basically which we are discussing is the logarithmic one, and subsequently we will see how they change depending on these parameters and the starting value of x and the delta x values. So, x starts from 1 and then the next value is 1 plus 0.5, which is 1.5, 1.5 plus 0.5 is 2, and it goes on. Again the number of data points is exactly the same, which is 124. I have kept it 124, which is a manageable number. So, obviously you can change it, as I said, to have a much better viewpoint that how the best fit line and the error terms and the values of the y1 value, which is the actual data which is being simulated, look like. So, based on the equation which I have with logarithmic 1, I have the y values. So, which is basically theta 1 plus theta 2 into ln of x. So, that the first value is 20, next value is 21.6219 and it goes on for each values. The error term is again basically the random variable generated depending on the ideas or which I just explained, which I will keep explaining for the error terms, and y1 is basically the obviously simulated data, the best fit line along with added to the error would give you the data points. So, when I plot it, the graph which I have shown. Now, let us consider that what happens with theta 2 being negative. So, theta 2 is basically minus 4 and theta 1 is plus 20. So, let us plot it. If it is minus 4 and plus 20, it becomes and just the opposite one. So, if you remember the convex and concave points which I have mentioned, they come out very easily as you keep changing the values of theta 1 and theta 2. The next value which you have is basically of a negative theta 1, which is minus 20, and a positive theta 2, which is plus 4. So, let us do it. This is plus 4, this is minus 20, and you get this curve, which is as I keep changing the values, the curves basically are plotted immediately, and as you have this simulated data and the Excel sheet in front of you, you can generate the data and find out many things. So, this is the graph. I am switching between the Excel sheet and the PPT file. So, this is the graph which you have in the Excel sheet for the values of logarithmic y and y1 versus x, considering theta 1 as minus 20 and theta 2 as plus 4. And if we see along the y axis, we are measuring minus 20, minus 15, minus 10, minus 5, 0 and goes on, and the error concepts are also very low. They are in the tune of about 0.5, 1 and so on and so forth. The last this graph which we have is the logarithmic case for y and y1 against x, for theta 1 is negative and theta 2 also is negative. So, let us consider that as minus 20, minus 4. So, again depending on theta 2, the graph changes from a convex to a concave, concave to a convex. So, again the values plotted along the x axis are in increments of 5, it goes on increasing, but starting from the negative direction, and the error terms are also as replicated. So, with this I will end this 46th lecture and continue with many such models which are there in the nonlinear regression. Switch between the PPT file and the Excel file where all the simulated data is here, such that you will get a hands on experience that depending on the parameter change for different nonlinear regression model, how the error plots are, how the best fit lines are, which will give you a lot more confidence in the concept of nonlinear regression. Have a nice day and thank you very much.